All right, welcome back. We're continuing our deep dive into electric machinery, focusing today on the synchronous generator. We're getting you exam ready, so let's jump right in.
So this right here is the central puzzle we're going to solve. You see, there's an ideal voltage that gets created inside the machine, but that's not what you actually see at the terminals when you connect a load. By the end of this, you'll know precisely what's causing that difference and exactly how to model it.
Here's our game plan. We're going to start with that ideal internal voltage. Then we'll look at how we can actually measure and characterize it in the real world. After that, we'll get into the big complication, armature reaction, and finally, we'll put it all together into the complete equation that describes how the machine really behaves.
Okay, first things first. Let's build a model for the voltage that's generated inside those stator windings when there's no load attached. This is our baseline, our ideal world. We call it the internal generated voltage, or E sub A.
The magnitude of this voltage, well, it all starts with a constant, K. This is what we call the machine constant, and it's totally unique to each generator. It basically bundles up all the physical design choices. The core's geometry, how many turns are in the stator windings, how they're laid out. It's basically the machine's DNA.
To that, we add phi. Phi represents the magnetic flux per pole. You can just think of this as how strong the magnetic field coming from the rotor is. And here's the key thing. This is the part we can actually control. We do it by adjusting the DC field current, IF, that we feed into the rotor windings. So more field current means you get more flux. Simple as that. And the last piece of the puzzle is omega. That's just the speed of the rotor, how fast it's spinning in radians per second. And this should feel pretty intuitive from Faraday's law of induction, right? The faster those magnetic field lines are cutting through the stator conductors, the bigger the voltage you're going to induce. So there you have it. The ideal voltage boils down to the machine's construction, the magnetic field strength, and the rotor speed.
So just to nail this down, K is the machine constant, it's fixed by the design. Phi is the magnetic flux, which we control with that field current, IF. And omega is just the mechanical speed of the rotor. Those three things multiply together to give us our ideal internal voltage, E sub A.
Now that equation is great and geary, but how do we connect the voltage we want to get with the current we need to supply in the real world? Well, that's where something called the open circuit characteristic, or the OCC, comes into play. It's a fundamental performance curve for any synchronous machine. And what's really cool is that this isn't just theory. What you're looking at here is a plot of actual measured data. To get this open circuit characteristic, you run the generator at its rated speed, but with no load connected. Then you just measure the terminal voltage, which is the same as E sub A in this case, as you slowly crank up the field current, I sub F. And you can immediately see two totally different zones on this curve. At the beginning, it's a perfectly straight line. In this region, if you put in more field current, you get a directly proportional kick in flux and voltage. But then, the curve starts to bend over. This is magnetic saturation. The iron core of the rotor can only handle so much magnetic flux. You can keep pumping in more and more current, but you start getting less and less of a return on your investment in terms of flux and therefore voltage. So why do we obsess over this curve? Because it's absolutely critical for actually operating a generator. This test is done on every single real machine. It's how you figure out the exact field current you need to get the voltage you want, and it's the core logic that automatic voltage regulators use to keep our entire power grid stable. Okay, so up until now, everything's been nice and clean, under no load conditions. We've figured out our internal voltage, EA, but let's be honest, a generator isn't doing much good if it's not connected to anything. So now, it's time to face the biggest real-world complication in our model, something called armature reaction. The second we connect a load, a current starts to flow out of the stator windings. We call this the armature current, IA. And here's the kicker. Anytime current flows through a coil, it creates its own magnetic field. And this is precisely where our perfect ideal model starts to fall apart. And this phenomenon has a name, armature reaction. The rotor is producing its magnetic field, BR. But now the stator current is producing its own magnetic field, BS. These two fields have to coexist in the air gap, and what the machine actually responds to is the net result, B net, which is just the vector sum of those two fields.
This diagram just illustrates the whole process perfectly. Take a look at panel A. That's our ideal no-load case, with just the rotor's field, BR. Now, in B, we connect a lagging load. A stator current, IA, starts flowing, and bam, it creates its own field, BS. Panel C is the key. The two fields add up as vectors. And you can see the new net field, B net, is not only smaller than the original BR, but it's also been twisted backward. The result of all this? That's panel D. The terminal voltage V phi, which is produced by this weaker, distorted B net, is now lower than our ideal internal voltage EA. Basically, the stator's own current is weakening and distorting the very field it needs to operate.
So we've seen the physical effect. Now let's do what engineers do best and build a mathematical model that can account for everything. We need to translate these magnetic field interactions into circuit components that we can actually analyze. Okay, so here's how we model it. We represent that voltage drop from armature reaction as an inductor, which gives us a reactance, X. The stator coils also have some flux that doesn't even make it across the air gap. We call that leakage flux, and we model it with another reactance, XA. Now, just to make life easier, we lump those two together and call the sum synchronous reactance, XS. And finally, of course, the copper windings have a little bit of resistance, RA.
Let's build this equation one piece at a time. We'll start with our perfect no-load world. The terminal phase voltage, V phi, is exactly the same as the internal generated voltage, EA. Now let's account for the load. That armature current, IA, is going to cause a voltage drop across our new synchronous reactance, XS. It is absolutely critical to see the J there. This tells us we're dealing with phasors and that this inductive voltage drop is 90 degrees out of phase with the current.
And finally, just for completeness, we subtract the tiny voltage drop across the stator windings resistance. This drop is right in phase with the armature current. And there it is. This equation now gives us the full story, the complete relationship between the voltage made inside and the voltage we see outside.
Now, if we just rearrange that equation to solve for the internal voltage EA, we get this. This is it, the complete synchronous generator model. It tells us that that ideal voltage, EA, is equal to what we get at the terminals, V phi, plus all those internal voltage drops caused by the machine's own resistance and synchronous reactance. So, we have our final equation. Why on earth did we go through all this trouble? Well, because this model has some really big consequences for how we actually operate generators in the real world.
And here it is, the big takeaway for anyone operating these machines. For most loads out there, which are lagging loads, like motors, armature reaction fights the main field and causes the voltage to drop. So to keep that terminal voltage steady, an operator or an automatic voltage regulator has to increase the field current to fight back. But for leading loads, the exact opposite happens. Armature reaction actually helps the main field, and you have to decrease the field current to stop the terminal voltage from climbing too high.
So let's just recap the three core equations we've put together today: how the ideal voltage is generated, how the magnetic fields interact, and finally, the complete generator model that accounts for everything. These are the absolute fundamentals. But what's the practical application? How do we use this final equation? Well, that's exactly what we're going to get into in our next explainer, 1C, where we'll build the equivalent circuit, draw out the phasor diagrams, and talk about voltage regulation and power ratings. I'll see you then.